Hi everyone, we're going to pick up in this video to discuss and wrap up the concepts associated with aqueous solutions. We just finished in the previous video talking about different ways that we can measure solution concentration, which is quantifying how much solute we have in a given solution. In practice, what we would do is we would make something called a stock solution, which is just a more concentrated version of that solution. And when we need the actual solution, we would dilute it. So for example, we would make a 12 molar stock solution, hydrochloric acid, and when we need the 1 molar solution, we would just take the 12 molar and add some solvent to it, which in this case would be water. What doesn't change when you do a dilution is the number of moles of the solute, because all you're doing is adding solvent. Now, because the number of moles of solute in the stock solution and the diluted solutions are equal, we can write the following equation, right? Which is just number of moles of solute is equal to in both solution. Remember that molarity is equal to number of moles over volume. So the number of moles would then be equal to the molarity times the volume. So what we end up deriving is this equation that's used to calculate dilution situations where we say M1V1, where the 1's correspond to the stock solution, equals to M2V2, where the 2's correspond to the diluted solution. Okay, let's take a look at an example of a dilution problem. We have a 122 milliliters sample of a 1.2 molar sucrose solution, which is diluted to 500 milliliter. And the question is, what's the molarity of the diluted solution? So it's always useful to have a drawing so you can imagine what the problem looks like. You originally have 122 milliliter, 1.2 molar solution, and it's diluted. So that means you're adding water to this until the volume now, after you add the water, is 500 milliliter. So the question is the new concentration. This is really a straight application of your dilution equation, which is M1V1 equals M2V2. We're trying to find the molarity of the diluted solution, so we need M2, which means we can divide both sides by V2, and that would isolate M2 to be M1V1 over V2. And all we need to do here is put in our values of M1, which is 1.2 molar, V1, which is 122 milliliter, and V2, which is 500 milliliter. Now, in some cases, I often see students like to change the unit of the volume to liters. In this case, it's really not necessary because, as you can see, the units will get canceled out. So whether you change it to liter or you keep it in milliliters, it would still get canceled out. The concern is when you change it to liter, sometimes people make a mistake in the conversion, and that causes you to get the wrong answer. When you do the calculation, you should get 0.293 molar, which makes sense. That's a smaller concentration than your starting value of 1.2 molar. We're going to close off this topic on aqueous solution by talking about doing stoichiometric calculations for reactions that happen in aqueous solution. The main thing about stoichiometry is we would need to convert our quantities into number of moles of our known and our unknown species. Now, in previous videos, we had talked about how to do that conversion from mass to number of moles using our molar mass. When we talked about gases, we had learned how to convert from pressure or volume into moles by using the ideal gas equation. Now we're going to talk specifically about the aqueous solution, and the new concept we learned here is molarity. So once we have molarity or molar concentration, we can also convert from volume to number of moles using the molarity of that species. And that's just based on the definition of molarity, which is number of moles over volume. So let's take a look at the example problem here, and I'm going to just explain it conceptually how you would do this. So you have a reaction between H2SO4, sulfuric acid, with sodium hydroxide, and the equation is already balanced for you. The question here is how much 0.125 molar NaOH do we need to completely neutralize or react with 0.225 liters of 0.175 molar H2SO4? So the question is really how much of this reactant is needed to react with that reactant. Now, when we have these type of problems in standard stoichiometry, we would have to convert them to number of moles first. Typically, we're given mass of some kind. We're going to do the same here. We're going to have to convert to number of moles, except that what we're given is volume and molarity. So to convert these to moles, you're going to have to multiply them, because remember, m times v is equal to number of moles. Okay, so that's the first step to do, is to convert that to number of moles. Now, once we have the number of moles of H2SO4, we can use our balance equation and the mole-to-mole relationship between the two reactants to calculate the number of moles of NaOH. So that's going to be our step 2. And then the last step then is to take that number of moles and the molarity of NaOH and use the molarity definition again to convert that to the volume of NaOH. Let's now take a look at a aqueous solution stoichiometry question. Here we are given a reaction between hydrochloric acid and silver nitrate, and we're asked to first write the balance equation and then answer a couple of stoichiometry type questions. So let's start with the balance equation. This obviously requires you to know nomenclature in order to be able to write these reactants. So HCl is hydrochloric acid, silver nitrate is AgNO3. Now, of course, the problem here is what are the products? Here is where you need to remember one of the other concepts we've talked about, which is the types of reactions. And when you have this kind of a reaction, this is a double displacement reaction where you have the pattern of AB plus CD forming AD plus CB. And so we're swapping the cations in this case. So that's what we will do. We would get AgCl and HNO3. And then from there, we need to find out what the states of each of those products is, and to do that we usually use our solubility rules. And so AgCl, if you check the solubility rules, ends up being a solid, and then HNO3, it's a strong acid, so it's just going to stay aqueous. Okay, and then the last part of it is to balance, but the equation is already balanced as is, so we're good to go here. I'm going to take a look at question B, where it says how many moles of AgCl is produced from 30 milliliters of 0.1 molar HCl. So if we have 30 milliliters and 0.1 molar of that reactant. So implicit in that question is the assumption that your silver nitrate must be your excess reactant and your HCl must be your limiting reactant, because they don't provide any additional information. To make that kind of calculation to get the number of moles of the product, you need to convert the HCl into number of moles first. So this is where we're going to need to use our molarity definition. Molarity is equal to the number of moles of HCl versus the volume of the solution. And so if we want the number of moles of HCl, then we can see that we can do a cross multiplication, or you can multiply both sides by volume. That would cancel out the one on the right side, resulting in m times v, as I said earlier. So once you have that, then you just take the molarity of HCl that you have, which is 0.1 molar, and then multiply that by the 30 milliliter. Now here's where you want to be a little careful. If you look at the units, molar, of course, means moles per liter. So it's really moles of HCl per liters of solution. And then here we have 30 milliliters. So the liter and the milliliter will not cancel. So that's where you need to convert your milliliter to liter. In this case, we would get 0.03 liter. And that would cancel out, giving us 3 times 10 to the negative 3 moles of HCl. And I should put a few more sig figs here. We can do that at the end. The last question is the number of moles of AgCl would just be the number of moles of HCl times the usual mole-to-mole ratio between AgCl and HCl. From the balance equation, we have 1 to 1, so it ends up being 3.0 times 10 to the minus 3 moles of AgCl. Let me take a look at the last question. It says here, how many milliliters of 0.1 molar HCl is needed to produce 17 grams of AgCl? So I'm going to erase this a little bit because they kind of switched the question a little bit here. Now they're saying, I know that I have or I want to make 17 grams of AgCl, and I want to know if my concentration of HCl is 0.1 molar, what's the volume in milliliter? So the way we do this is kind of reversing the steps we did here in the previous problem. We start with the mass of AgCl, so we need to convert the mass of AgCl to the number of moles of AgCl. This is for part C. First, we find the number of moles of AgCl, which is going to be 17 grams divided by the molar mass, which is 143.32 grams per mole. And this ends up giving us this many moles of AgCl. Once we get the number of moles of AgCl, we can use that and the balance equation to calculate the number of moles of HCl, because that's the thing we're interested in. And as we saw earlier, this ends up being a one-to-one stoichiometry. So the answer is going to be identical. Okay, so then the last step is to figure out the actual volume. So for that, you're going to need your molarity definition. So molarity is equal to number of moles of HCl. Molarity of HCl is equal to number of moles of HCl over the volume of solution. So if I need to get volume, then it's a bit of algebra. I'm going to have to multiply both sides by volume of solution. When I do that, I end up getting volume of solution times molarity equals number of moles. And then I have to isolate the volume. So I'm going to divide both sides by molarity of HCl. So that's like an algebraic operation. And so what I end up getting is this. Volume of solution is equal to number of moles of HCl over the molarity of HCl. The number of moles I already have from my calculation. The molarity is given to us as 0.1 molar. So we would write that down. And remember that 0.1 molar is the same as 0.1 mole per liter. And this is how your units cancel out. And then you have 1 over liter, which just becomes liter. And so your final answer is 1.19 liter of solution. In milliliter, this would be 1.19 times 10 to the third milliliter.